Hi guys. Okay, now this is the moment. We have to draw the shear moment diagram, and we have this. Let me fix this thing. Everything's gonna collapse in my desk. Okay, you find this thing here, and somebody asks you, "Oh, draw the shear moment diagram," and you say, "Of course, this is so easy. I'm the master of shear moment diagram." Until you start trying to calculate the reactions, and you realize that this is a statically indeterminate. Why? This is a fixed support, right? So you have AY, AX, and MA. And this is a roller, BY. When you start counting, and you said, okay, remember that we covered that before, and we said, how do we determine if something is statically determinate or indeterminate? And we say number of reactions, and we compare the number of reactions with 3 times the number of bodies. And how many reactions do we have? 1, 2, 3, 4 reactions, and only one body from here to here. So 3 times 1, 3. When the number of reactions is bigger than that, that's a statically indeterminate. And 4 minus 3 is 1, so that means that it's a statically indeterminate of first degree. Now it's different, because now I want to calculate, I want to draw the shear moment diagram, but I don't know. First I have to find the reactions, the external reactions, in order to do that. And then this is where what we were covering before, the method of compatible deflections, or the method of the forces apply. Consistent deformations also is called, or flexibility. The first step is selecting one redundant. As I said, we're going to select one redundant. Why one? Because it's first degree. If it's more than first degree, then we have to select 2, 3, 4. But that's a nightmare. That's really, really long. So just for exemplifying the method, let's say this is only 1 degree of indeterminacy, because it is what it is. And first you have to select the redundant. The redundant is the extra reaction that I can take out, and still this will be stable and statically determinate. For this particular example, this part, I'm going to select the reaction in Y, the roller, as my redundant. This problem I will redo later on, and I will select the moment as the redundant. Where in this particular case, what you couldn't select as a redundant is the reaction in X, because if you do that, that will be free to slide in this direction, and that will become unstable. But you could select BY, you could select even AY, and you could select the moment, but not AX, never ever. So for this particular case, I'm going to select my redundant as BY, meaning we're going to have now this structure like that, and this is going to be the same load, and this structure will deflect following something like that. At the moment, at the point where my reaction B on my roller was placed, I know the original deformation should be 0, but here you're gonna have a deformation delta B. Remember, the deformation for this should be something like this, kind of. So here the deformation is 0, but in this one, which is called the primary structure, as we said before when we use virtual work, primary structure, then you're gonna have a deformation delta over there. Now, what is the next step? The next step is, I know this is happening, but I know it's not supposed to happen, so I want that to happen. How do I make this to be that again? I push this up. And that's exactly what we are doing here. We're gonna be pushing that up at that point with a force equivalent to By. But I don't know how much is that force, so I'm going to use a unit load for this one. When I use a unit load for this one, this is supposed to deflect something like that. And this value here is how much deformation happens at the point B when I apply a unit load in this direction at the point B. So that's called also FBB, and that's called flexibility coefficient. Now, the total deformation has to be 0. So 0 has to be equal to this delta B plus what I need to push this up. And in order to push this up, what I need is, if I push it with 1, I get FBB. If I push it with BY, I get BY times FBB. And from here, we can solve for BY. BB. Okay, good. One of the things that I didn't say for this first problem, EI, let's say that is constant. Good. Now we are ready and good to go. So first step, calculate the deflection coming from the primary structure. Deflection. So let's call this a step, I don't know. This is step 1, right? So let's call this step 2. Deflection at B, because this is the point that we're interested in the primary structure. How do you calculate that deflection is up to you. Your professor probably is going to ask you to use a particular methodology for that. You can use virtual work, you can use area moment, you can use conjugate beam, you can use tables for that. You can use Castigliano. But for this example, because I'm interested in you practicing virtual work, so we're going to use virtual work. Virtual work. How do we calculate that? Remember, if you remember the principle of virtual work, it says that the external work, which is the external virtual load times the external displacement, is going to be equal to the summation of all the internal values and the summation of all the internal M over EI dl, where M is the virtual internal virtual moment produced by the external virtual load, and this is the real deformation produced by the moment. So let's do that. We have this. I'm interested in knowing at that point. So what do? I have to do something to define this structure completely. And that is going to be, if this is the point B, I'm going to need to do 2 cuts. I'm going to use a cut 1, 1, 1, and I'm going to use a cut 2, 2, like that. I know this distance is 0, this is 15, this is 5. So let's start with this cut 1, 1. If I'm going to use the cut 1, 1, I could calculate these reactions, but I'm lazy. I don't want to calculate those reactions. So I'm going to look at this portion here, like that. And this is the point B. The distance from here to here is 5. And I'm going to call this distance X in this direction. Because I'm using this side of the beam, this part, remember this is a vertical load, distributed load of 0.5 kip per foot, and I'm using this side. So if I'm using this side, I'm gonna get this a big M in this direction and a shear in that direction over there. So if we do that for 1, 1, which by the way 1, 1 means from here to here, 0 to 15. So if we're gonna do that for 1, 1, then we can do summation of moments here. If we do that, summation of moments there, equals 0. Then if we do that, remember this is a force here coming from this distributed load, and it's gonna produce a concentrated force. I don't know how much is that, but it's gonna be a concentrated force over there. The distance, the force is gonna be 0.5 multiplied by 5 plus x. And the location, I don't know if it's gonna be here or here, depending on the x, but it's gonna be x plus 5 divided by 2. So once you have that, you can basically do summation of moments here, and if we do summation of moments there equals 0, then you have negative m minus this 0.5 times 5 plus x multiplied by the distance, and the distance is 5 plus x, or x plus 5 is the same, divided by 2. So m is going to be equal to, this is going to be negative, pass it to the other side, negative 0.5 divided by 2, and this is going to be 5 squared plus 10 times x plus x squared. Or I can apply this to this thing, and then I can say that the moment is going to be equal to negative 0.25 x squared, because this is 0.25, and 10 times that is negative 2.5 x, and this is 25 times 0.25 is negative 6.25 minus 6.25. Okay, that's my equation for the moment 1, 1. Now I know that this is not necessary, this is not needed. However, I'm gonna do it as if I didn't know, because I want to explain you. So if I use now my section 2.2, because I'm gonna calculate it, then what I have is basically this, like that, and then I'm gonna have my moment, my shear, sorry, this direction, my shear, this is my load, this is the distance x, and this is from 0 to 5, because I'm just from 0 to 5. And if I do that, then I know this force here is going to be 0.5 x, because remember that load is 0.5, and my moment, the distance is x divided by 2, and then I can do summation of moments there, and then you get m, or negative m minus 0.5 x multiplied by x divided by 2 equals 0, m equals negative 0.25 x squared. And I just wasted my time doing this, and you're gonna see now why. Okay, we have this part here, but this is the virtual work, this is the deflection of the primary structure. Now we have to do the other part. The other part is what? We're gonna calculate, we're gonna put the unit load over there, the external load. I'm gonna use the same paper here, I don't want to keep killing more trees. So I'm gonna do that here, same thing, 15.5, and here now I'm going to put my load, my virtual load, or my unit load over there, because I did that, so I'm gonna use the same type of cuts, 1, 1, 2, 2. Now for the virtual structure, remember this is called the primary structure, and this is the virtual structure. Now if I do that for the virtual structure, I'm going to use this color for the virtual structure, and I'm going to use a, for section 1.1, section 1.1 here, same approach. I'm going to put the section 1.1 here, I'm going to put my load of 1 there, this distance is x, this distance is 5, this is going to be my moment, a small m, small v, and then I'm going to do summation of moments here at this point. If I do summation of moments at that point, then you're going to have negative m minus x equals 0. Is that correct? Negative m times x equals 0. Yeah, Yeah, that's correct. So m equals negative x And remember, this is for section 1, 1, 0 to 5 in the virtual. And for section 2, 2, what I have is this. Nothing. M, V. So M equals 0. And that's what I said, you know, that I wasted my time when I did that, because now that I multiply these two, I'm not going to use this for anything. I only needed this section 1, 1, to define everything. Okay? So now we put this together in order to calculate the deflection. I'm still working in the primary. Still working for the primary. Working for the primary. So now 1 times delta, or delta in this case, is going to be the integral of big M negative 0.25 x squared minus 2.5 x minus 6.25. This is what we have here from this part, and this is supposed to go from 0 to 15 multiplied by the other one that we calculated, which is just x, negative x. Negative x we just calculated here, negative x. This is the same section 1, 1 for virtual. dx, and remember this is divided by EI. And in this case EI is constant. So we can solve for this, we can do the whole thing, we can put everything in the calculator, or calculator, as you want to call it. And then we're going to get that the deflection at B is going to be equal to negative 6,679.7 divided by EI. There you go. And this, basically, what it's telling you is that it's downward, like that. That's what is happening here. The deflection over there is going to be downward. When I do it, you know, if you realize, probably it's going to give a positive value, but you know that we assume the deflection coming down because it's coming down, so that's negative. And that will be the deflection for the primary structure. Now the next step is, what step is this? Step 1, step 2, step 3. Step 3. The step 3 is calculate FBB. What is that FBB? What is my page? Where is my page? I always say that I have to clean this thing. Here. FBB. We calculated this one. Now we need to calculate this one. But look what happened. This, we already have it. We just did it. Oh no, we didn't do it because the load in the one we did was like that. So what? I just changed the signs and that's it. So my moment here is gonna be x, no matter what, if I put like my equation like that. So basically, for this step, I already have it, and I can do the same thing. The virtual work. 1 times FBB equals the integral from 0 to 15 of m times m is the same. The virtual and the real structure for this part is the same, divided by EI dx, or integral of 0 to 15 of x times x divided by EI dx, or x to the third divided by EI from 0 to 15. That's basically it. So my flexibility coefficient is going to be 1125 divided by EI. Now, what is the next step? Apply our equation. What is our equation? Our equation is our consistent deformation equation. 0, why 0? Because here the displacement is 0. 0 has to be equal to delta B plus FBB times BY, or we can solve for BY. And BY is going to be equal to negative delta B over FBB. Done. Delta B, this one. FBB, this one. So BY is going to be minus times minus is positive, 6679.7. EI and EI cancel out, divided by 1125. So BY is going to be equal to 5.94 K. Yay! Nice. And we calculated our BY. Now, what do we do after we have this BY? Then we go to our original structure, which I would love to know what it is. Really. It's creepy sometimes. People steal things and there's nobody here. Okay, here. 4. Now, go back and to statics. How? We have this. This was our original structure. And that's what we're going to do. We're going to come back to the original structure here with one big difference. And the big difference is that now I'm recording a video. I can talk right now. 0.5 kip per foot. And I know what is the value for, let me hang this out. Okay, good. I know the value now for the reaction because I just calculated that reaction and the value was 5.94. So I put that value over there. By equals 5.94 kip. And I can perfectly calculate now my moment and my reaction, which this reaction is going to be MA and B AY, and this is going to be 0 because there's nothing else going on in X. Now what do we do? Do statics, as I said. What do we do with the statics? Okay, first I need the distances. 15, right? Yeah, 15, 5, like that. And we can do summation of forces in Y equals 0. Okay, then you have AY, and then you have this force from the rectangular distributed load, which is 0.5 minus 0.5 times 20 plus 5.94 equals 0. So I can solve for AY, and AY is going to be equal to, calculator, this is what, 10 minus 5.94, 4.06 kip. What is the next step? Summation of moments. Okay, summation of moments at A equals 0 in order that I calculate the moment, this moment here. So I'm gonna have MA positive plus 5.94 times 15, this one, and then I have 20. I have somewhere here in 10. I'm gonna have this force, which is 20 times 0.5 is 10. So I'm going to have minus 10 force times 10 distance equals 0. And then you can solve for your moment. 5.94 times 15 minus 100. That's 10.9. MA equals 10.9 kip feet. Now, reactions completed. What is the next step? Draw the shear moment diagram. Shear moment diagram, I shouldn't even be doing it, but I really like doing them. So let's do a shear moment diagram. You put your lines, discontinuities, points of interest, whatever you want to call it, at the beginning, at the end, wherever you have an internal support, whatever the internal force, or whatever the distributed load begins, wherever the distributed load ends, wherever you have a change in geometry, then you do that. And now you put here your shear diagram. AY, remember, is 4.06, MA is 10.9. I'm not gonna do axial because there's no axial. You go start with this point, you find this force here, 4.06, and then what happened? 4.06 minus this area, which is 15 times 0.5, so 4.06 minus 15 times 0.5 or 7.5 is negative 3.34, negative 3.44. Straight line, straight line, straight line. And I find this one now that is gonna push it up, plus 5.94. Go back, 0.94, and that's 2.5. And then you have this force here, which is rectangular. 0.5 times 5 is negative 2.5. Closing zero, and everybody say yes. Now the moment diagram is similar, right? You start with this moment here. Where is the moment? 10.09. 10.09, but because it's in this direction, it's gonna be negative. It's gonna jump down 10.9. That's my moment here. I know this value. If I wanna cheat, it's not cheating actually. This is knowing it. If I wanna know this one, I know this area is gonna be 2.5 times 5 divided by 2. That's 6.25 positive, meaning it has to start here in the negative, because when I add this, it has to go to 0. So I'm just teaching you how to cheat, guys. I don't know if you remember this circle, but it will be nice if you remember it. This is please don't neglect infants, neglect dumb people instead. You can refer to my statics channel for that. And this is basically positive decreasing, negative increasing, negative decreasing, positive increasing. This here is positive decreasing, positive decreasing, positive decreasing, like that. And the value, we say that it was 6.25. The only thing that I need to know now is this, and this is what? Positive decreasing, so it has to go like that. And this is negative increasing, so this has to go and do something like this and come back like that. Now, I'm not calculating that value, of course, but now I have to calculate that value. How do I calculate that value? In order for me to calculate that value, the first thing that I have to do is find this point. How do you find those points? You can do a triangular relation if you want, and you can say that what I like to do, I'm going to explain it again. What I like to do is this. If this is the shape that you have over there, which is not quite, but let's assume this is the shape that you have over there, and this is 4.06 and this is 3.44. What I do is I draw this line here, and then I know this is 4.06, so this is 4.06, this is 4.06, and then in that way I can say, oh, look at that, 344 plus 4.06 is related to this distance. What is this distance? This distance is 15, the total distance, as this 4.06 is related to this distance. 3.44 plus 4.06, that should be, by the way, 7.5. So 7.5 is as 15, like 4.06 is at this distance x that I'm looking for. So x is going to be equal to 4.06 times 15 divided by 7.5, which I don't know why I didn't multiply by 2, and that's equal to 8.12. So x equals 8.12. This distance is 8.12, and now we can use areas again, the method of the areas, and we can say that negative 10.9 plus this area, that's gonna be 8.12 times 4.06 divided by 2, is positive minus 10.9. That's going to be 5.58, and that value over there will be 5.58, and then everybody say the big yes. And the problem is completed. Now, I'm going to do this problem again, but now I'm going to select the moment as redundant. See you in the next video. Watch the next video, because you never know when you have to switch your redundancy.